particle P is moving on a smooth horizontal plane. So I'm just going to sketch it out. Okay, and it's got constant acceleration, and then we're given some other information. I just want to say a couple things. So it says I and j are horizontal unit vectors. So it could be, for example, that I is going in this direction, and j is then perpendicular to it going in this direction. J here is not like going up from the table or anything. And we don't need to look at weight. The weight is presumably balanced with the normal reaction. And then all we need to focus on is it moving in these two dimensions. So the key thing is, again, it's constant acceleration. So we can apply Suvat, but this time in 2D. So A is going to equal 2.41 in vector form. And then when t is 0, it passes through A. Okay, so here's A, and then it's going to B. But we've got a fixed origin, which is maybe down here. So we're looking at vectors. We'll come into that in a minute. We're told that the velocity of P as it passes through A, so that's the initial speed, is going to be minus 16 minus 3. And then find the speed of P as it passes through B. So that is when the time is 5. So I can apply V equals U plus AT, which is going to be minus 16 minus 3 plus 2.51 times 5. That gives 12, 5. And hence I get minus 4, 2. But we're asked for the speed, so it's going to the left and up to start with. I mean, we don't actually know that that is necessarily the case, but this is a good enough representation. We're going to be applying Pythagoras, so it's going minus 4, 2. Speed is going to be minus 4 squared plus 2 squared, square rooted. This is the square root of 20. I think the mark scheme allowed an exact answer, but we're going to presume, we're modeling this situation. It's a particle, for example. So I wrote it to three significant figures, 4.47 meters per second. Then we're told the position vector of A. That's the one that I identified before, going from O to A. And we're then told at time t equals capital T, P passes through the point C. Okay, so it's going to be going further along this surface, extend it, and it's going to get to C. Well, I can do very similar. I can write down my Suvat again. You don't actually really need to, it's basically the same. It's just now the time is not equal to 5 anymore. Okay, and then S is going to be, um, well, okay, I could write down S, but the best thing to do is write down S equals, well, it's going to be UT plus half AT squared. And it's going to be the initial position vector. That's going from O to A plus UT plus a half AT squared. What I mean is I could subtract these and work out how far it's gone, but there's no real need. It's just easier actually to go straight to this formula. Then we've got 4C, because that is our final position vector at C, capital C. And that is going to equal 4T4 minus 10 plus minus 16 minus 3t plus a half a, which is going to be 1.2 and 0.5 t squared. So it must be the I components are equal and the j components are equal. We don't know all the j, so we're going to need to deal with the I first. So I components 4 equals 44 minus 16t plus 1.2t squared. So 1.2t squared minus 16t plus 4t is equal to 0. And then this mechanics question, don't start trying to, factorize it or multiplying so that it factorizes. It does in fact factorize, but let's just put it in the quadratic formula. 1.2 minus 16 and 40. This gives us 10 and 10 over 3, 3.3 recurring. But we are told that t is greater than 5, so I'm going to reject that one. Although the position vector has that I component at 10 over 3, it's not in the same place necessarily because the y component could be different. But in any case, we're just going to reject it, and t is equal to 10. So now I can look at the j components and work out c. So c is going to equal minus 10 minus 30, because that's minus 3 times 10, plus 0.5 times 10 squared. That's going to be 50, which is 50 minus 40, giving an answer of 10 as well. Well done.